Hello everyone, welcome to this fourth part of the lecture series of the molecular modeling lecture series. Now in the previous parts you mostly dealt with sort of static calculations where the nuclei are fixed in space and you were doing some density functional theory calculation, for instance. And this changes now in this part. So here we let the atoms move. So we go from statics to dynamics, and we would like to know and understand how we can do that, because we know, after all, the atoms are not sort of static objects, but they move in time. Now that requires us to go through a couple of things and approximations. The molecular dynamics that I will introduce relies on two approximations. One is the Oppenheimer Approximation, which I will discuss in some detail. Then after that, the classical approximation of the nuclear motion. So these two things give us molecular dynamics. Classical molecular dynamics, and then I will discuss some time-stepping algorithms, integration of the classical equations of motion, and then I will talk how we can combine molecular dynamics with density functional theory calculations to do ab initio molecular dynamics, or DFT-based molecular dynamics. And I will explain in detail how in such schemes the nuclear forces are calculated. And here I will go through the Hellman-Feynman theorem, which is very important in that respect. And then we'll very briefly introduce ensembles and thermostats. So I will explain how we can do calculations and simulations at a well-defined temperature. And then I will, at the end, we'll talk a bit about property calculations. All right, so let's start with Oppenheimer, with the Oppenheimer approximations and some preliminary considerations at the beginning. I'd like to start with a question. Now, when we draw a molecule, and many of us have drawn many molecules in our life, we usually indicate only the positions of the nuclei, but not the positions of the electrons. So why is that? And here I give a nice example of a molecule, very complicated for the people who care about it. It's an N-type semiconducting material in one of the best organic solar cells to date. Now, we usually think of electrons. The reason is, of course, because we usually think of electrons zipping around the nuclei, not the nuclei zipping around the electrons. So why is that? There's, of course, an intuitive answer. It's the same reason why the Earth, we imagine the Earth, orbiting the Sun, not the Sun around the Earth. It's because the nuclei are heavy, electrons are light, therefore the electrons are faster than the nuclei, and they will sort of instantly adjust to nuclear motion. And this is just here at the bottom left. I draw a little cartoon. So imagine you have the nuclei 1 and 2, and then you have the electron cloud. And as the nuclei change position, the electrons, since they are very light, they will sort of instantly adjust to the change of the nuclear positions, and therefore this electron cloud here, as the two atoms come closer together, also the electron cloud will contract, and we will not see a picture like this where the electrons just remain invariant to what the electrons are doing, to what the nuclei are doing. Okay. Therefore, in some sense, the nuclear positions determine what the electrons are doing. And therefore we are not, we just leave them out when we draw a molecule that's as complicated as this one. So the question is, where does this all come from? And how can we understand or justify this from first principles. Now, if we talk about first principles, we have to write down the Schrödinger equation that governs everything that happens with electrons and nuclei. This is what I've done here in equations 1 to 2. So this is the time-independent or stationary Schrödinger equation for a full coupled electron nuclear problem comprised of m electrons and n nuclei, H psi is equal to E psi. The Hamiltonian here contains the usual terms. So the kinetic energy term of the nuclei, kinetic energy of the electrons, and then all the Coulomb interactions between electron-nuclei, electron-electron, and nuclear-nuclei. The wave function, importantly here, is not an electronic, not a nuclear wave function. It's a coupled, full coupled electron-nuclear wave function, depending on all the nuclear coordinates, capital R, and all the electronic coordinates, small r. Okay. Now, how does this picture of electrons tracking nuclear motion arise from this equation? How does it arise? So this is not obvious. I mean, if you look at this equation, it doesn't just follow from that, right? So this is the Oppenheimer approximation. This approximation applied to that fully coupled equation gives us the picture of electrons zipping around the nuclei. Right. So what is it? I first would like to present the physical picture. So now we start by doing the following. So we write down this coupled electron-nuclear wave function as a simple product of an electronic wave function, which depends on the electronic coordinates and only parametrically on the nuclear coordinates, times a nuclear wave function, psi of r. Okay, and if you insert this, and we will show this, if you insert this simple product into the fully coupled Schrödinger equation that I shown in the previous slide, and you assume that the mass of all the nuclei is much larger than the mass of the electrons, one obtains a much simpler Schrödinger equation. And this much simpler Schrödinger equation is shown here in equation 4. And this is just the Schrödinger equation for the nuclei. Okay? Here is the kinetic energy operator of the nuclei. Here is something which I will explain in a minute. It's called potential energy surface. It's just a scalar function acting on the nuclear wave function. And then the usual eigenvalue equation, total energy times the nuclear wave function. So now what happened to all the electronic terms, to the electronic wave function, to the kinetic energy of the electrons, to all the interaction terms? Well, they are all folded effectively into this potential energy surface, ER. Okay, so they are all contained, so the effect of all of that is contained in that potential energy surface. And this potential energy surface is a very complex, multidimensional scalar function. It depends on all the 3n nuclear coordinates. That's written down explicitly here in equation 5. And of course, you can make a lower dimensional cuts, and one lower dimensional cut of a typical potential energy surface is shown here in that picture for a small molecule. Where you typically plot the potential energy here as a function of some nuclear coordinates. And this potential energy surface has minima and maxima and transition state, and this is where all the nuclear motion is happening. Okay, and there is all electronic wave function, all this, it's all gone, it's all contained into that in that potential energy surface. Okay, what I would like to say further is that it's actually quite straightforward to formally define the conditions required to go from that full coupled Schrödinger equation to that nuclear Schrödinger equation with that potential energy surface in it. It is much more difficult to actually mathematically justify these conditions. Okay? So indeed, the picture, the validity of the Oppenheimer approximation actually comes from experimental verification. And we also know that in certain cases, this Oppenheimer approximation breaks down. And this typically breaks down whenever you have electronic states that are very close in energy compared to the thermal energy. So that's the case in very high temperatures, thousands of Kelvin, for instance, or when you do photoexcited calculations, or when the electronic states are near degenerate. Okay, so in all these cases, then you have to be very careful applying the Blumberger approximation. Is most likely not valid there. Okay. Now I would like to go a little bit more in detail how one can actually derive the nuclear Schrödinger equation from the full coupled problem. And this is really just an outline, and I recommend to you to go through this in detail if you haven't done this before. So it's just a few steps, and I really just would like to sketch that. So in the beginning, what you do, you write down your fully coupled wave function as a sum of products of electronic wave functions, which I call psi Ri, and note that these electronic wave functions still depend parametrically on the nuclear coordinates, so have different values for each nuclear configuration, times a nuclear wave function that only depends on the nuclear coordinates. And what I should say, these electronic wave functions here, you choose them so that they are eigenfunctions of the time-independent electronic Schrödinger equation for a fixed set of these nuclear coordinates R. Okay, so this is shown here. So this is the first step, and in this step there is no approximation. So this is exact. It's actually called the Born ansatz for that wave function, and you can do that. The problem is you have to include an infinite number of these products. Okay, but there is no approximation. And the second step, you make the first approximation, and then you say, okay, I remove all the terms with electronic wave functions that are not the ground state. So I only keep the ground state wave function. And so then you only end up with a single term here for the ground state potential energy. And then you insert this into the fully coupled electron-nuclear Schrödinger equation. And then you just get this this equation 9. So we have done nothing else than just inserting the single product into the Schrödinger equation. Now, third, and this is the second approximation, we look at the mass difference. We consider now the action of these kinetic energy operators here on that single product. And note that both the electronic and the nuclear wave function, they depend on the nuclear coordinates. So if then the nuclear kinetic energy operator acts on that product, we have to apply the chain rule. So it's Tn times psi plus Tn times phi. Now the kinetic energy operator for the electrons also, of course, acts on this product, but the nuclear wave function does depend on the electronic coordinates, so we are only left with one contribution. So it's these three contributions. And we look at the mass difference. Remember that the kinetic energy operators, they have their mass in the denominator. And for this operator, we have the nuclear mass in the denominator. For this operator, we have it in the, here we have it in the denominator. So that kind of implies that this term here, with the large mass in the denominator, probably leads to something much smaller than this term here. Okay, so this is written down here in equation 11. So this could be a good approximation. Now in the Oppenheimer approximation, one assumes that this is actually the case, and in addition, uh, one assumes that this term here is zero altogether. Okay? So this, the Laplacian, if you like, of the electronic wave function is assumed to be zero. The Laplacian with respect to the nuclear quarters. And that's it. So if you assume that, you insert this all into your equation 1, then you get just a pure nuclear wave function with that potential energy ER. Okay, that's the so this is very easy to show, and the above arguments they imply, of course, that the Oppenheimer approximation is exact in the limit of infinitely heavy nuclei. It's usually a very good approximation for systems in the electron neutral state because of the large photon mass compared to the electron mass. Okay, so that's all for the with regard to the Oppenheimer approximation. In the next slide, I will introduce the classical description of nuclear motion. Thank you very much.